Hello, everyone. Uh, Welcome back. Yes. So we are going to address some of the issues that we had in class today to help you guys understand a little better. Hopefully, you don't have any problem with the theory of the chapter 3 and chapter 2 and chapter 3. But to solve these problems became a little confusing, a little problematic for me as well as you guys. I think I made it a little more confusing for you as well. So what I did was I went back and talked to the author of the book, and he reached out to me. We talked a little bit, and we were able to clear some of the confusions. But again, as I have stated before, I will be using SI units first of all. Sorry, SI units. Or if not SI, I will be using consistent units in any questions you may get, right? So this is the first thing, but you want to be able to solve the book problems as well, and you want to be able to you want to make sure that you are correct in solving the problem. So most of the issues we have had is with the convergence, unit convergence, and as well as these two parameters that we have here, WAF and WAP. We had the discussions in class. Each of us had their own opinion, and I'm going to address those right now. And we are going to solve part A, part B, and part C of the problem 3.3 of the chapter 3 together. Not together. I mean, I'm going to solve it for you. Please reach out to me if you had any questions. If the confusion still remains for you guys, if reach out to me if you were still confused or if you had any other questions. Okay, so first of all, let's address this mass flow rate controversy that we have had. I don't remember which one of you guys had this opinion, but one of you guys had the correct opinion that WAF is actually the fan. Let's call this W fan. The fan mass flow rate. Okay, only the fan part, so the bypass. So that in the terminology that we are going to use, this WAF, let me actually, is the bypass mass flow rate. Okay. And WAP is the engine core mass flow rate. Okay, so what does it mean? It means that let's say you have this turbofan, you have your engine core here, that's where the compressor starts, compressor inlet, and the engine exhaust. You have the fan exhaust here, and you have the total flow coming in. I'm going to call this total flow the fan mass flow rate, if you will. I'm going to call number 1. Number 2 is going to be the fan exhaust or the bypass mass flow rate. Exhaust or the bypass mass flow rate. And number 3 here is going to be the engine mass flow rate. So based on what we have discussed, this is going to be m dot 2. Okay. WAF is your fan exhaust or the bypass mass flow rate. And this is going to be your m dot 3 engine mass flow rate. So the total mass flow rate coming in to your turbofan will be m dot 2 plus m dot 1. Okay. So this is the part 1, and we are going to address the second part in the during the solution out to this problem. So the problem is telling us that this turbofan is described by its internal pressures and temperature as well as air mass flow rates and the mixed jet velocity, which we have here. And we want to examine a few parameters for this engine for a ballpark approximation. Okay, so keep in mind that this engine is a little different from what we have seen before, what we have seen in the other problems. In the other problems, your fan had a separate exhaust. Your fan exhaust was somewhere here, right? Which in one problem it was a station 13, in another one was a station 19. But the fan exhaust in this problem is at the same station as the engine exhaust. Okay, so this problem fan exhaust same as engine exhaust. Okay, and whenever we are from now on, whenever we I know we decided on a different thing in the class, but let's change that. From now on, whenever we say fan, we are talking about the bypass. So whenever I use the word fan, this is what I mean, the bypass flow rate, right? It is highly possible for me to use it as the total mass flow rate coming into the turbofan, but if that was the case, please correct me in the class. I don't want to create any more confusions. Okay, so yeah, let's see what we are supposed to do. The first part is asking us to estimate the fuel flow rate from the total temperature rise across the burner, assuming the heat value is 18,600 BTU per pound mass, and the specific heat at constant pressure is 0.24 and 0.26 BTU per pound mass degrees Rankine. Okay, so if you want to take a look at, we are essentially looking at a station 3 and a station 4 from this problem. A station 3 and a station 4 for part A. Okay, and this is where we have our QR put into the system. Right? This is the combustor, this is the burner. Yeah. So if you want to write an energy balance for this case, your energy balance is going to look like this. We are going to have m dot whatever energy coming in, which is the m dot naught or m dot air, the core engine, multiplied by HT3 that is coming in. So we have to subtract this from m dot naught plus m dot f HT4. That's the total enthalpy at the station 3. That's the energy at the station 4. This is the energy at the station 3, right? It's going to be equal to changes in the internal energy. How do we calculate the changes in internal energy? That's the heating value, QR, multiplied by your m dot f. Okay. So but we don't have the enthalpies. What should we do? From the previous chapters, you know that the total enthalpy is going to be equal to Cp multiplied by the total temperature. Okay, so we replace that in these equations for HT3 and HT4. So we are going to get m dot naught plus m dot f Cp4 Tt4 minus m dot naught Cp3 Tt3 is going to be equals to m dot f QR. Okay. So the other thing, when you are solving the problems of this chapter, or in general, whenever you are dealing with the British units in this book, that's actually I talked about this with the author of the book as well, and he basically told me that's how you deal with British units. You just have to be always mindful of the unit conversions. Okay, so we are given in the problem, Cp is given as BTUs per pound mass degrees Rankine. Okay, so BTU per pound mass degree Rankine. Okay, again, BTU per pound mass degree Rankine. Okay, which is going to be multiplied by a degree Rankine for temperature. Again, degree Rankine for temperature, so these two cancel out. Okay, and then it is multiplied by an m dot. But because we have the m dots at both sides and they're going to have the same units, we don't really care about that. So the unit you're going to get on the left hand side is going to be BTU per pound mass multiplied by the m dot unit, whatever that is, feet per second, feet per hour, pound per second, pound per hour, or whatever, because that doesn't matter because we have the m dot on both sides, right? But whatever your unit on the left hand side is, this multiplied by whatever is the unit of m dot. So we should have the same exact thing on the right hand side, okay, which we already have. We already know that QR is 18,600, right, BTU per pound mass, right here. Okay, so we don't really need to care about the units here. The units are consistent. But the other thing we can do to simplify this matter a little bit is to divide all of this equation, all sides of the equation, by m dot f. So, and m dot by m dot o, m dot f divided by m dot o is going to be equal to f, which is fuel mass to air mass ratio, fuel mass flow rate to air mass flow rate ratio. Okay, so if you divide everything by m dot o, here we are going to get m dot o over m dot o, which is 1, m dot f over m dot o, f, m dot o over m dot o, 1, m dot f over m dot o f. So we are going to have 1 plus f cp4 tt4 minus cp3 tt3 is going to be equals to f multiplied by qr. Okay, plug in the values. 18,600, cp4 is 0.26, cp3 is 0.24. We have, for the total temperatures, we have them in degrees Fahrenheit. tt4 we have it as 1720 degrees Fahrenheit. Just add it by 460 to convert it to Rankine. For tt3 we have 800. Just add it by 460 to convert to Rankine. So if you do the analysis, you are going to get F equals to 0.0147. And this time I've done the calculations myself before posting the lecture, so I'm not relying on the solution provided by the author. So that's good. And the next part, this first part has asked us to find the fuel mass flow rate, right? To find the fuel mass flow rate, we have to go back to the definition of F, which was m dot f over m dot o. But the m dot o given to us is in this form, so we are essentially looking for w dot f over w dot ap. Okay, right here, which is 150 pounds per second. So 0.0147 equals to w dot f over 150. So w dot f is going to be equal to 2.19 pounds per second. Part C. Part C is asking us to find the thermal efficiency of this problem. Thermal efficiency of this case. Okay, so what we discussed in class was that thermal efficiency is essentially changes in mechanical energy, let's say mechanical energy over the input energy, which in this case is m dot qr, m dot fqr, right? Total input energy. Here, in this case, we don't have any shaft information, so we just assume that the changes in the shaft, the changes in mechanical energy that has gone to the shaft power is negligible. We just care about the kinetic energy. M dot F QR. Okay. So changes in the kinetic energy, it can be calculated by using the exhaust. Whatever exhaust, let's say sigma Ke exhaust kinetic energy minus sigma K inlet kinetic energy. Okay, I. And this is a notation that I use. I mean, I haven't seen it anywhere, so just for you guys to better understand. Okay. So what are the exhausts here? We have, let's go back to the engine. We have the engine exhaust right here. We also have, I'm going to use another color for this. We also have the fan exhaust. And keep in mind that this is a circular exhaust, right? We have the fan exhaust as well, or the bypass exhaust, right? The idea was, in this specific case, the exhaust velocity of the fan is V9, and the exhaust velocity, the exhaust velocity of the engine is also V9. Okay. The exhaust mass flow rate of the fan is going to be W dot AF 165. The exhaust mass flow rate of the engine is going to be W dot AP in this case plus W dot F. Okay. So these are the exhaust kinetic energy is related to this mass flow rate and the velocity, as well as this velocity and this mass flow rate. Okay. So for the fan or for the bypass, we can write M dot AF V9. This is going to be your exhaust over there. And keep in mind, it is V9 in this problem, only in this problem, because the exhaust of the fan was the same exhaust as the engine, and we are assuming that the velocity is going to be equal. It is not necessarily the case always, but in this problem we are saying that it is. Okay. Plus M dot, this is actually W dot AP plus W dot F multiplied by V9. Okay. We can actually rearrange this. We can say W dot AF plus W dot AP plus W dot F multiplied by a V9, which is your exit velocity. But what is the inlet kinetic energy? The inlet kinetic energy is essentially whatever is happening here, okay, at a station 0 or a station naught, right? So minus M dot naught plus multiplied by a V naught. Okay, what is this M dot naught? Is essentially going to be W dot AF, the fan or the bypass mass flow rate, plus W dot AP. Okay, so I hope this has solved the conflict. And keep in mind that we are assuming it's a perfectly expanded nozzle here. And this is actually V squared over 2. The kinetic energy is V squared over 2. Okay. And then you just have to divide this by M dot or W dot F QR. M dot F, which is in this case is W dot F. Okay. So what you need to investigate that is going to replace your quiz is what to do with this problem. With this V dot, because we don't have V naught, right? What should we do? All right. The idea is if you have the total temperature and the static temperature and the CP, which you do have, you should be able to find a velocity. I remember in class, one of you guys brought up the fact that where should you find the CP? That's the CP of the air. So it is a standard heat capacity. But if you couldn't find the CP, please reach out to me. I will give you a value for CP for at the sea level temperature. And then you can just use that in calculations. But you shouldn't have any problem finding this. In an exam or a quiz, you will be given these parameters, right? So I won't expect you to go out there and find that like CP at the sea level temperature, unless that's the goal of the problem. But I don't see how this is going to be a point of a problem. But so the idea is if you have the total temperature at station 0, static temperature at the station 0, and CP at the station 0, we are just going to call it CP, you should be able to find V naught, right? Based on the equations you have already seen. Okay. And you eventually you have to tell me whether it is a good idea to assume V naught is 0 or not. Is this wrong or right? Okay, that's the idea here, and I want you to be able to answer this question and to be able to back it up with some sort of a calculation, right? But the problem doesn't really end here. The problem is actually, as I've mentioned, the biggest problem and the biggest confusion is the units that are being used here. Okay. So W.F is actually pounds per second, right? So let me actually rewrite this here. Let's call it we have it right here. Let me back up a little bit. This is pound per second. Let me use another color. Pound per second, pound per second, pound per second, and V is feet per second. This 2 is dimensionless, right? So V squared is feet squared per second squared. And this WF is pound per second. QR that we are given is BTU per pound mass, or BTU per pound. Okay, that's 18,600. This is what we are given. Okay, so these units, this addition of units, they actually cancel each other out, right? We don't need to be concerned about those. And we want to get to a dimensionless parameter. Efficiency is dimensionless. Okay. So essentially, you just have to be mindful of the fact that on the numerator, you have feet squared per second squared. And on the denominator, you have BTU per pound mass, right? You have to find the conversion parameter. And it is easy to look up online and find this. But I'm going to give you this conversion parameter, right? So 1 BTU per pound is equals to 25,037 feet squared per second squared. Okay, you just have to make sure that you either transform this value to feet squared per second or transform this value to BTU per pound mass, and then find the efficiency. If you plug in the values, if you do the calculations, your efficiency should be somewhere around 32%, in that ballpark area. Okay. So I hope this very small lecture has addressed all of the confusions. And I just want to keep it small. So if you have any questions, please reach out to me, and we'll try to go over this again together. Okay. See you on Wednesday, and have a good rest of your day.